Hey guys, today we're going to be talking about how temperature and humidity, so basically climate, affect sound. Now, in this video, we're going to be combining a bunch of ideas from things that we've talked about previously. We're also going to be using a little bit of the chemistry that we've used before. So if you haven't had chemistry, don't freak out too much. If you don't remember anything from chemistry, don't worry about that. I will remind you of the most important principles from chemistry that are going to be important here. All right? So let's go straight into it. The first question we have is, does temperature affect sound? The answer is unequivocally yes. The reason why is because temperature is directly proportional to the average kinetic energy of the molecules in your gas. All right, this is something hopefully you learned in chemistry. So when you heat up a gas, what that actually does, and when we measure temperature, it's really just a direct relationship of how fast those molecules are moving around. So what does that mean? Well, it means that as the air gets hotter, the molecules are moving faster, and therefore they're able to transfer the sound much more rapidly. And so the result is that sound travels faster when it's warm. All right? So that's pretty straight up. Temperature is proportional to the average kinetic energy of the molecules. More kinetic energy means more speed. More speed means that the sound can travel faster. Piece of cake, right? Now, the second question today is a little bit harder, but we're going to address that anyway. Does humidity affect the sound? Now, in order to answer this question, we have to talk about, well, what exactly does humidity do to the air? Now, a lot of people think that humidity makes the air heavier. That's actually not true. It might feel that way, but it feels that way because of the way that our lungs interact with the air that we're breathing in. It interacts differently with water than it does oxygen and the other gases that are in the atmosphere. We might feel that way because it makes us sweat. Humidity makes us sweat, so we feel heavier. But the air actually is not heavier. Let me show you. What is air actually made of? Right? Well, hopefully you know air is made up of nitrogen. And it's about 78% nitrogen. It's made up of oxygen. And it's about 21% oxygen. Right? And this is if there was no water. It's 78% nitrogen, 21% oxygen, 1% argon. And then that pretty much uses everything up, right? There are small percentages of other things like carbon dioxide and helium and all these other gases that are in our atmosphere, but they're not big enough for us to worry about when we do this. Now, why do I talk about this? Well, you may have learned about molecular mass or atomic mass in chemistry class. Now, each atom in a gas, this is important, in a gas, at a specific temperature and pressure, you have a certain number of molecules or a certain number of atoms present in that specific volume. Okay? Now, by changing the makeup, by using larger atoms or larger molecules, it's not going to change the number of molecules that are there. It's just going to replace some of them and move things around a little bit. All right? So it's important to understand that we're going to have the same number of atoms or molecules no matter what. And so if we add water in, if we make it more humid, we're not just taking what we have and adding more in, it would more or less be replacing some of those atoms with water. So the question is water heavier or lighter than the atoms that we have here, the molecules that we already have here? So nitrogen at 78%. Nitrogen is made up of two nitrogen atoms actually that are together. You never find it by itself. A nitrogen molecule always has two nitrogen atoms that are connected together. Now the molecular mass of a nitrogen molecule, two nitrogens together, one nitrogen has a mass of about 14 grams per mole. So when you put two of them together, it's 28 grams per mole. It doesn't matter that it's bigger, you still are going to get the same number of molecules inside of a certain area volume. Inside of a mole. So what we're going to have is that this is 28 grams per mole. And if you don't understand the moles or anything like that, don't worry about it. It's not a big deal. You can just pay attention to the numbers here. All right? we've got oxygen, which is the next biggest thing in our atmosphere. Oxygen is 16 grams for one of them, but oxygen, just like nitrogen, always comes in pairs. It's always two oxygen atoms that are connected together to make an oxygen molecule. So oxygen, even though one is 16, two of them together is going to be 32 grams per mole. All right? And then argon, which is one that we usually kind of ignore, but argon is about 40 grams per mole. Now, argon is actually a larger atom, and it doesn't need to pair with another argon. So it's just one argon atom that's going to be 40 grams per mole. All right? Making a video. Just practicing, man. I got to practice for class.
I thought it was going to be like AP Physics 2, so I was going to come in and be all excited about the elements. But yeah.
Nope, sorry. That was Mr. Kelly. All right, here we go. So we got 40 grams per mole of argon. Now, the big deal is this. When we add in those water molecules, it's not being added into this, making the air heavier. It actually is just going to come in and it's going to replace some of the molecules that we already have. You can still only fit a certain number of molecules into a specific volume based off of the pressure and temperature and everything else that you have there. So the number of molecules is not going to change. Here's the thing, water. You all know that water is made up of one oxygen and two hydrogens. Now we talked about earlier that one oxygen just by itself was 16 grams per mole. Hydrogen is really light. That's the lightest element. It's only 1 gram per mole. So if we have one oxygen, which was 16, one oxygen, which was 16, two hydrogens, which are 1 each, that then adds up to 18 grams per mole. Now again, even if you don't understand all this mole stuff, don't worry about it. You should be able to see that out of the most common elements that are inside of our atmosphere, the most common molecules, the one that is the least heavy is water. So if I actually make the air more humid, that water is going to take space of some of these heavier molecules, which means that the air is actually lighter. The air is actually less dense when there's water. Now, what does this have to do with the big question of, does humidity affect sound? Well, again, let's come back to, remember, sound is a longitudinal wave. In a longitudinal wave, one particle comes along and it smacks into the next one, which then moves forward. That's a collision. And remember, in a collision, we have to conserve momentum. So if you have a particle, a heavy particle that comes in and slams into a lighter particle, what happens? What happens if momentum is conserved with a smaller mass? Remember, momentum is equal to mass times velocity. If you have a smaller mass, it's going to have a higher velocity. And just like with the temperature, remember the temperature, if we had higher speed of particles, that meant that the sound could move faster. Same thing here. Because some of those particles, the water particles, are smaller, it's going to allow the sound to move faster through the air, which means that sound travels faster when it's humid. How about that? Now, there is kind of a neat side effect of all this. Okay? When any wave travels faster, it tends to bend a little bit more. Right? Sound spreads out, and we're going to look at this in another video, that sound spreads out as it travels. And as it changes from one medium to another, it bends. And you've probably seen this before with light, when you put your straw in your cup and it looks like the straw goes in here and then ends up over there. Try it if you're not sure what I'm talking about, but I think most of you know what I'm talking about. You can see that the light looks like it's coming from different places. That's because of the bending of light, because light travels at different speed in the water and in the air. Same thing here. Sound will travel at different speed, at different temperatures, at different humidities. The faster that it travels, the more that it bends. Now what that means is that if it is hot, air is going to travel faster. If it's humid, air is going to travel faster. So on a hot, humid day, the sound is actually going to bend away faster, which means that it's not going to be able to be heard as great of a distance away because it's spreading out that energy. Remember, a wave is transferring energy, so that energy is spreading out further, right? It's bending away from where I meant for it to go. On a cold, dry day, because it's cold, it's going to travel slower. Because it's dry, there's less water, it's going to travel slower because of the larger, more massive molecules bumping into each other, right? It's going to travel slower. So on those days, it's not going to bend as much, it's going to go further in the direction that I meant for it to go. And so kind of that byproduct of these two things is that based off of these temperatures, based off of the climate, sound, not only does it go faster and slower, but we might be able to hear it further away. When it's cold and dry, we can hear it further away. When it's moist, humid, and hot, then the sound isn't going to travel as far, or at least we're not going to be able to hear it as far because it bends and dissipates more. All right? So hopefully that was interesting to you, and we'll touch on a few more of your questions in later videos. See you later.